Good afternoon, everybody. We're running on time again, so I'll just introduce here Nick Coghlan is a CPython core developer on the board of directors for Python Software Foundation, and he's going to talk to you this afternoon about Unicode.
Thanks. Make all strings be Unicode. 5 little words that have had a profound impact on the last 7 years of my life. So I've been a CPython core developer since 2005. And those 5 words are from the original PEP 3000, so now called PEP 3100. And that's where the core developers started accumulating all of the non-controversial Python 3 design changes. So things that became obvious that in the course of maintaining Python 2, they were just broken, that they caused lots of problems in lots of obscure ways that they ended up getting escalated to the core developers to say, why is my code broken? And yeah, explaining why was because the core data types had broken. And so Guido started the Python 3 project in earnest in 2006, and then Python 3.0 was released in 2008. 7 years later, we're still dealing with some of the consequences, and we still have quite a ways to go. So one of the interesting questions about Unicode was, why did we change the default? What was actually wrong with Python 2? And we hear that a lot from people who do a lot of network and soccer programming, because they're like going, no, the 8-bit strings were awesome. They worked really well. So I'm going to switch to a little demo. And so you can see here we've got 3 data files to play with. This is going to be interesting. So 3 data files. So let's start up. We'll have Python 2. Start up Python 2. There we go. So we're going to import pandas to do some data analysis. So we have some CSV files. So let's read our English data. Help if I actually store the data somewhere. Right. Data. There we go. Okay, so we've got our data file of student data results. Yeah, I don't actually use pandas very much. I know I should, but yes, if you're doing data analysis, use pandas. Don't reinvent all their wheels. So anyway, so pandas is pretty cool. Okay, let's get the results out for Kelly. Okay, so we have Kelly's test results. And if we want to get the results out, if we've got that as a 8-bit string, we can get it out. We've got it as an 8-bit string, we can get it out that way. If we've got it as a Unicode string, we can get it out that way. Okay, so now I'm no longer teaching in Australia. I'm an Australian teaching in Japan. So my Japanese isn't very good, so I've transcribed all my students' names into Romaji. And so now what I'm going to do, instead of reading the English data, I'll read it in Romaji. So now our data, instead of Harry, Kelly, and Naomi, we have Haruto, Keiko, and Nanami. Okay, it's still pretty cool. We can still get all our data out the way we used to. So that all still works. But okay, I'm no longer an Australian teaching in Japan. I'm an actual Japanese teacher, and I want to use Python to analyze my students' results. So I'm actually Japanese, and so I'm going to write their names properly. So here we see Haruto, Keiko, Nanami. And one of the interesting things about Haruto is there's 3 different ways of writing Haruto in kanji. And they all transcribe to Romaji as the string Haruto. which would mean that if I had 3 Harutos in my class and they all spelled their names differently, even as an Australian, my trick of translating to Romaji wouldn't have worked. But it gets worse. So now I don't actually have the ability to enter kanji on my keyboard, so I'm going to have to find my mouse pointer. Yes, I'm cheating, I know. But copy and paste works fine. So we'll go with that. So now we're going to go and say, hey, that column access trick was pretty cool. Let's try that. Ah, no, that doesn't work. What about 8-bit strings? That works, cool. But maybe we should be handling our data as Unicode. Well, so our Japanese teacher's not going to be pretty happy at this point. So I think we can agree at this point there is something wrong with Python too. So I'll get back to my presentation. So yeah, Python 2 defaults to only handling English text. It really is an English native programming language. Sometimes it will get the non-English handling right. So we saw there Pandas dealt with the Japanese data quite happily. We could actually get our Japanese data out using the 8-bit strings and the lookup sequence. And if I'd continued on, you can actually, if you have a Unicode string and you explicitly encode it to UTF-8, it'll do the right thing. But it just gets messy. Like things that you take to advantage when dealing with Python 2 in English just don't work right when you switch to another language, especially Asian languages. And so it causes problems for data-driven analysis tools like Pandas, and it also causes problems when people are learning Python. So there's a wonderful post on Stack Overflow when they announced, on the Stack Overflow blog, when they announced the Portuguese language version of Stack Overflow. And the point they were making was that they had a lot of students in non-native, in countries where English was not the native language, and there was a huge barrier to entry where you had to learn English before you could start learning to program. And that was a real problem. And so what they wanted to change it to was, in a language like Python, the keywords, while some of them are inspired by English words, in practice you can learn a lot just by treating them as magic incantations that tell the computer to do something. And so when you're learning in another language, you can actually teach all of the concepts in the kid's native language and just not worry about the fact that the keywords are inspired by English. And Python 2 really doesn't do a great job of supporting that model because a lot of the times, like, the kids can't even use their own name as a variable. And so if your demo variables are Harry, Kelly, and Naomi, sure, you're fine. If you're wanting to get Haruto, Keiko, and Nanami to use their own names, you kind of have to tell them to use them in English, which isn't what you want to be doing. So that's not a Python problem. That's a computing problem. That it's one small part of a much larger pattern where computers, a lot of what is modern computing today was born in the English-speaking world, and it reflects that heritage. And one of the core principles guiding the evolution of computing has been making them better at communicating with and between humans, rather than the original days where it was the humans that had to adapt to the computer. However, a lot of the legacy of that history is still with us today. And it goes back as far as the telegraph. So some aspects of Unicode date back to the invention of Bordeaux code almost 150 years ago. And so Bordeaux code was a system used to send telegraph messages between teletypes. And it's also the origin, so teletypes are also the origin of the TTY abbreviation you'll sometimes see in Unix computers related to the screen and the keyboard. And so Bordeaux's code was adopted by Western Union for the telegraph in 1901 and standardized as the International Telecommunications Alphabet number 2 in 1930. So that's a picture of that there. The entire code, 5 bits, 32 characters. So 32 characters wasn't enough. And so ITA2 is what's called a modal encoding, where you can see the figs and the letters control characters actually shift the encoding to a different mode, where you're either sending letters or you're sending figures. And modal encodings are actually problematic, because if you're transmitting data in a modal encoding and the far end misses your shift character, then they're receiving nonsense until the next shift character you send. And so what that ends up meaning is, so this, however, what it does mean is you can actually transmit stuff very efficiently. And so ITA2 is actually still used today for high-frequency communications, so HF radio. And that's because your bandwidth is so low that the 60% overhead of going from 5 bits to 8 bits per character isn't something you can afford. You really want to compress it that much. But in terms of the history of the impact this has on Unicode, you can see that null, line feed, carriage return, and the good old bell character that makes a bell ring are all already there. Space at this point was considered a control character. It got turned into a letter later. And there's actually another variant of this, or a derivative of this, that keeps the letters and figures page. But it's the Russian MKL2 standard, which adds a third page for Cyrillic characters. However, so very, very limited character set, all uppercase, no lowercase letters. So hence the telegram thing of only doing uppercase letters. And we have this problem of it's a modal encoding, so very, very vulnerable to transmit errors. So come to the early 1960s, and people wanted room for more characters. They wanted to do lowercase. They wanted more punctuation symbols to play with. And so in the 1960s, we got the American Standard Code for Information Interchange. One of the interesting things here is this was almost an 8-bit encoding, because one of the neat things the 8-bit encoding would have given you is that you could fit 2 binary coded decimal characters in an 8-bit sequence. They ended up going for 7-bit because 8 bits was too long, and they couldn't afford the 16% additional overhead of using 8 bits for every character. And again, a lot of this was driven by how slow transmission channels were. That it was just, when your transmission channels are getting measured in tens, maybe hundreds of bits per second, if you're really lucky and have a really clean line, bits matter. And so it became 7-bit. And that's the full ASCII chart. Again, 128 characters, fits on a screen. So you can, again, we can kind of see some of the ITA2 control characters have carried through. Reflecting the geopolitics of the time, the pound symbol from ITA2 has been replaced by the dollar symbol in ASCII. So you power shift from the UK to the US there. And some of the details of the layout, again, relate back to transmit channels. So they're related to what happens under high bit error rates and what gets confused with what when bits go wrong. And then other things relate to certain kinds of categorization. So like shifting from uppercase to lowercase, for example, is a matter of flipping a single bit. And that was done deliberately to make certain operations more efficient. However, very much English only. And so we ended up with this notion of extended ASCII. And people were like going, we're already to a point where computers are tending to use 8 bits. And so people have gone, right, what do we use that extra bit for? And we say, well, we'll use it to indicate that we're using the other 128 characters. And so what happened here was people went, oh, okay, well, we'll use it to teach the computer additional languages. And so they used those extra 128 characters to add in things like Cyrillic characters, more of the letters from the Latin alphabet, different currency symbols for different parts of the world. And so this actually worked pretty well for European languages and Cyrillic languages. Didn't work at all for Asian languages, and Africa wasn't even on the computing world radar yet. that dealing with African languages just wasn't a problem people were considering. And so we ended up with a whole lot of different codecs. And if you want to look for popular ASCII and compatible codecs, you can look to Asia. And so things like ShiftJIS, Big5, ISO 2022. So Yeshik Chang's CJK codec pack was actually added to Python 2.4 back in 2005. And with the addition of that and various other codecs that have been added over the years, the Python standard library now supports over 100 different language codecs. So problem solved, right? We've got codecs, people can use all these different languages, everything's fine. No. What codecs basically give us is they give us the ability to make computers bilingual. And so the computers can speak English, and they can speak whatever language the primary owners of that computer use. And that's great if computers never talk to each other, and if we never transfer files between computers. Why would anybody ever want to do either of those? So networked computers completely mess up this model. Portable media completely mess up this model. And the other thing is, even within a computer, it causes serious problems for translating between languages. And similar tasks. So you can, if your task is translate between English and language X, or between language X and English, sure, a bilingual computer can handle that. But if you want to go from, say, directly from German to Japanese, Japanese to Chinese, something written in one of the Indic scripts, or translation within India. I don't know how many scripts they have, but the number of languages is hard enough to count. So bilingual computing was useful in terms of making computers useful to people, but really wasn't good enough. And so what we really wanted was multilingual computing, where we could deal with any language at any time, or more accurately, all the languages all the time. And so a way of representing any human language in the world, but we also needed a transition plan from the existing ASCII-based infrastructure. And so we come to Unicode. So Unicode was invented in the early 90s by engineers from Apple and Xerox. So if you think the Python 3 transition is taking a long time, try working on Unicode. And the initial attempt at defining this was 16-bit only. And the trick they'd done to try and get things to fit into 16 bits was that they left out a lot of the old and unused kanji and han characters. Problem. Things have had names for a very, very long time. So these old and unused kanji and han characters were used a lot in proper nouns. So people's names, family names, cities, towns, you name it, those were used somewhere. And so pretty soon, as soon as the engineers put this idea forward, it didn't take long from after the formation of the Unicode consortium for them to realize 16 bits aren't enough for everybody. And so current Unicode is expanded out to 21 bits. So currently it looks like 21 bits is enough for everybody, including all of the Japanese telcos emoji systems. But yeah, so problem solved now, right? Like one codec to rule them all? Yeah, no. So I'm going to completely ignore the geopolitics of the fact that there are some additional there are some additional codecs primarily used in China. We'll just live in our happy Unicode-only world for the moment. But even within the Unicode world, there's still 3 codecs of interest. And it turns out that choosing between choosing your in-memory, your on-disk, and your wire protocol encodings has lots of interesting trade-offs. And the 3 major codecs have emerged to deal with those different cases. So UTF-8, UTF-16LE, UTF-32. The big selling point of UTF-8 is it's the only one of the three which is ASCII compatible. And so there's a whole bunch of interfaces where ASCII compatibility is mandatory, that you will just break too much stuff if you use an ASCII incompatible encoding. And so ASCII compatibility basically means any code point that is shared with ASCII looks the same in UTF-8. So those original 7-bit ASCII encoding is identical in UTF-8. And the key advantage, as I said, is that it means that if you have protocols which are breaking on ASCII characters and where the ASCII characters are semantically significant, you can often flip those to UTF-8 and the new UTF-8 characters will just pass through just fine. And so this is most obvious in things like POSIX file system encodings, a lot of network protocols, HTTP, SMTP, that kind of thing. They can often switch to UTF-8 from ASCII, and things will just work. And the other thing is that this is also a very efficient protocol for ASCII-heavy protocols, which is, again, a lot of those network encodings. And so this became the most popular encoding for public HTML sites in 2008. Preferred local encoding on POSIX systems, including OS X. And in the mobile world, we see it in iOS and native mode in Android. So UTF-16LE, its main feature is optimizing the basic multilingual plane. So the original 16-bit Unicode is called, that's its name now, and includes almost all commonly used characters in modern languages, place names aside, emoji aside. And so it uses 2 bytes for the basic multilingual plane, 4 bytes for everything else. And so it can be more efficient than UTF-8 for non-English text. So if you're dealing with primarily Japanese text, primarily Chinese text, this will actually use less memory than UTF-8 will, depending on the details. And so it's the preferred local encoding on Windows, the .NET CLR, and the JVM. Oddly enough, so the wide Windows APIs. Oddly enough, these are all APIs invented after 1991. And it's also seen in the Dalvik and ART runtimes on Android. And then the final one that's widely used is UTF-32. And so the thing about UTF-32, computers are still really, really good at processing regular arrays where every unit of data is the same size. Both UTF-8 and UTF-16LE are variable width encodings. Some of the code points take more space. And so you don't get simple array data out. And so instead, you have to work with those as if they're file-like streams. And so you have cursors and pointers into your data array. You have mappings to figure out where your code point boundaries are. And if you split in the middle of a code point, weird things can happen. As anybody who's ever stored a UTF-8 encoded string in MySQL can likely attest to. So anyway, and so one of the problems with this is simple array-oriented algorithms become error-prone. And you can see this if you ever use Python 2 in narrow mode, which we do by default on Windows in Python 2. There's certain strings, if you try and work with Unicode data that goes beyond the basic multilingual plane, we will actually get it wrong. And that's true for a lot of other Windows and Java code. However, the nice thing about UTF-32 is that it lets you use the simple array-oriented processing algorithms that were designed for binary data, and you can apply them to text as well. And this is what we do in CPython, the reference interpreter, to share algorithms between binary, 8-bit binary data and text data. We make sure that we store the text data in a fixed width format, which, worst case, goes out to UTF-32. So after all that, so all of that messy history, where did Python 3 get us to? So let's get back to our demo screen. So let's get out of Python 2, drop into Python 3. So we'll grab pandas again. So I'll skip over the English and Romaji data and go straight to the Japanese. Japanese. Yep. So we have our data. And this time, so we can read out the column. We can read out that, and if we're still using a U prefix, we can read that out as well. And so in Python 3, it just works. We had to completely retool the text model of the language, but it just works. So, yep, back to my Prezi. Not that one. That one. Okay, so, yeah, so we actually fixed the problem. Getting actually people to the new version of the language with the problem fixed is still an interesting challenge, but that's not what today's talk about. So yeah, so user space processing is actually in a pretty good place. One of the interesting challenges we had in designing Python 3 was figuring out which of the 8-bit string operations were text only, and which only made sense for, which also made sense for binary data. One of the more controversial decisions we made there was deciding that all interpolation operations, so both dot format and printf style mod formatting, deciding both of those were text only. After several years of experience, we've come to the conclusion that while that was correct for dot format, for the printf style mod formatting, that's actually really, really useful in the binary domain as well. And so one of the features in Python 3.5 is bringing back binary interpolation. So bytes objects in Python 3 have a mod operator that basically works very, very similarly to 8-bit string interpolation in Python 2. And that was one of the keys for the Twisted and Mercurial folks. We spent a lot of time with them in the last couple of years. So yeah, so that's bringing in binary interpolation back is a big thing for code that's dealing with network protocols and file system formats. So how much time?
That's it.
Oh.
Questions?
Okay.
Are there any questions?
Yeah, we'll go with questions.
I'd like to come up here to the microphone and feed it in.
Oh, okay. I'll do the system boundary stuff then. So yeah, so user space is in a pretty good place. We're bringing binary interpolation back. Most of the interesting challenges that remain are still around system boundaries and interfaces with other libraries. So Mac OS X, as you'd hope, with Apple being co-inventors of Unicode, and the only inventors still around, Mac OS X is actually in a pretty good place, and it's because they just made UTF mandatory several years ago. They said, look, UTF-8 is it, don't use anything else. And the nice thing this let us do is we just hard code in CPython that if we are on a Mac, we assume the system encoding is UTF-8. I think there are still some quirky issues around some of the graphics libraries, especially tkinter. But aside from that, Macs are in pretty much the best place of them all. With Apple being one of the big drivers of Unicode, that's kind of as you'd hope it would be. So Windows took an interesting path in their Unicode adoption, which is they brought in a completely new parallel set of APIs. So if you are still using the old MBCS APIs, your stuff does not handle Unicode correctly, end of story. CPython has mostly switched to the Unicode compatible APIs, and so most things work. Unfortunately, one of the things that we haven't switched yet is our console handling, so the interactive prompt and various aspects of that. There's a PyPI project called Win Unicode Console, which deals with a lot of that, and their README actually explains a bunch of the things that don't work under the hood. And then we can also occasionally run into problems with bundled libraries like OpenSSL, which which they're written for the POSIX world where they assume UTF-8 for everything, which isn't necessarily the way we're dealing with them. So yeah, Windows in a pretty good place, but you'll still find some rough edges. And then on Linux and other POSIX platforms, one of the interesting problems here is that they don't have a central entity like Apple that can say, right, UTF-8 is it, you're not allowed to use anything else anymore. And so there we have to try and figure out from the OS what the system encoding is. If the OS gives us correct data, everything is pretty much fine and dandy. If the OS tells us the wrong thing, then we will believe it. And this does not end well. So systemd sets it reliably. Upstart and others can sometimes get it wrong for cron jobs and service daemons, and they'll tell us to use the default POSIX mode, also known as lang=C. This was designed in the 1960s and assumes you want to use ASCII. So if you're, yeah, so it just, if we end up in a situation where we're falling back to the POSIX default, we get it wrong. So we've got some stuff in 3.5 where we try and mitigate that a bit better, but it's still fundamentally the OS is telling us the wrong thing. And while we may be a bit more skeptical now, we still fundamentally believe it. And the reason for that is that glibc will believe it, and us disagreeing with glibc about what the encoding is actually an even bigger problem than us disagreeing with the OS. So earlier versions of Python 3 did try disagreeing. We eventually went, no, we just have to go with whatever glibc thinks. We're still working on getting c.utf8 locale into upstream glibc by default. Once that happens, then there'll be a much easier option where we'll potentially fall back to c.utf8. So, yeah. And I think
right
we're really
thank you. We're out of time, so thank you very much, Nick.